So if I have a simple, dielectric, this is enough for me to explain how the response looks like. Let's try to see, this is numbers, right? It's some equation. It doesn't give us any intuition. So let us try to plot this and see what happens. Okay. The first thing we can do is, if you look at this equation, I just rewrote that equation here or on the previous slide. Let's consider the situation first in the extremes. Okay. So let's say, what is the epsilon at zero frequency? Epsilon at zero frequency is going to be, if I put omega is equal to 0, I'll end up with 1 plus chi susceptibility plus omega p square by omega naught square. Excuse me. Yeah. Okay. And what is the epsilon at large frequencies? When omega goes to infinity, what should be the epsilon? In this case, of course, the second term, this omega is going to blow up. So 1 over omega is going to be 0. So you end up getting 1 plus chi. Okay. And if you combine these two, we see that always epsilon of 0 should be greater than epsilon of infinity. Okay. And how much should it be greater? It should be greater by omega p square by omega naught square. Okay. You might say, why are you interested in this? Well, it turns out that right now in this week, we are studying naturally occurring materials. Okay. But then we'll slowly introduce the concept of artificial materials in the subsequent weeks, wherein, because if you look at only the naturally occurring materials, our toolbox is quite limited. Okay. We are limited by what nature gives us, but we don't want to stop there. This whole idea of metamaterials, to engineer the response of materials to electromagnetic waves, is centered around creating new materials which have desired functionality. Now, when you're trying to engineer new materials, you should know how the response will look like. If not, you'll end up getting some data which is not correct. Okay. To the extent that, I've had PhD students who graduated, let's say, looking at metamaterials, and they measured these parameters. Epsilon and real and imaginary parts are something that you can measure. Okay. Or rather, you measure imaginary part and you compute. Okay. I will come to that slightly later on in this week. But when you measure that, you have to ensure that some certain basic rules are consistent. Okay. If not, the whole exercise is wrong. And when you are trying to push the limits, it's very easy to make mistakes. Okay. So I believe that whoever is working in the area of understanding nanophotonics, I think some of these things are very important. Okay. That's why the emphasis. Okay. So now, omega naught is greater than, epsilon at 0 is greater than epsilon at infinity. Okay. And if you actually take, we plotted out this equation. So in this case, we plotted the Lorentz oscillator for a value of chi is 10, and we assumed gamma by omega naught of 0.05. With these values, we plotted out, and this is how it looks like. So you have the real part, which is in blue here, and the imaginary part. Okay. And what we said is, of course, at 0 and infinity, there is no imaginary part. So only the real part. So you see here, this is my epsilon of 0. And this is my epsilon of infinity. And epsilon of 0 is higher. Okay. How much is it higher? Well, if you look at epsilon of infinity, it is close to 10 here. The 10. That's because the chi was 10, so 1 plus chi. So 11 should be the number. It's very close here. We can't see it in this axis. Okay. Whereas at 0, it is going to be some number which is higher here, depending on how much, is my gamma greater than, or, the number of gamma by omega naught. That will determine how much is this here. Okay. And you exhibit a very curious, this exhibits a very curious time dependence in frequency of this form. And this is known as a Lorentzian line shape, because Lorentz model is coming from that. Lorentzian line shape. Okay. So the real part behaves this way, and the imaginary part exhibits a peak at the resonant wavelength, where omega is omega naught. You see a very sharp absorption peak. Okay. And now the width of this absorption peak is essentially your gamma. This width is defined by gamma. So I'll just show in a moment how, if gamma is changed, this width will change. Okay. And should also note that the real part exhibits a peak slightly below omega here. I mean, this should be omega minus gamma by omega naught, and another dip minimum at omega plus gamma by omega naught. Okay, there is this slightly skewed distribution. Okay, so this is what epsilon behaves like. And I said already that sometimes we look at epsilon, sometimes we look at refractive index, right? So if you calculate, we previously talked about the expressions relation between the refractive index and epsilon. If you remember, we said that refractive index is simply going to be this complex quantity. I'm just repeating it. Refractive index is n plus ik or n1 plus n2, and that is n square is going to be epsilon r, right? So from that we saw that we got an expression epsilon 1 is equal to n square minus kappa square, epsilon 2, which is let me move this up, epsilon 2, which is 2n kappa. Okay, this is what we got. And so we can substitute this into the expression and we calculate. One of the first things we notice is now we are talking of n1 and n2, which are essentially n and kappa. I deliberately am using multiple terminologies just to ensure that you are familiar with all of them. Okay, it doesn't matter. You should be able to think of all of them simultaneously. Okay, so now if you look at the refractive in the real part, the behavior is similar to epsilon 1. Okay, so effectively if you look at the numbers as well, n, the real part, or rather n1 is proportional, it's almost equal to root of epsilon 1. Okay, it's going to be exactly root of epsilon 1 when kappa is very small. Okay, away from the resonance it's going to be exactly root of epsilon 1, because this is my kappa right here. Epsilon 1 is n square minus kappa square. If my kappa is going to be low, n is exactly root of epsilon 1. Okay, in the close to the resonance it's going to be slightly different, this is going to be slightly different, yeah. But overall if you look at, let's say in this case my peak, right, is going to up to about, let's say 40 something. In this case it's going to about 6 plus something, right? So roughly we are in the square root regime, right? 49 is square root of 49 is 7, so close to 7 is where we should be. Okay, so the real part is exhibiting exactly the same behavior as epsilon 1, and the imaginary part exhibits a dependence which is close to, kappa is close to epsilon 2. It's similar to epsilon 2. Okay, why is that valid? Well, we said, for let's say low losses, well, epsilon 2 by 2n should be equal to kappa. Okay, so if you are assuming small losses, roughly this should be the number. Epsilon 2 is epsilon 2 by 2n should be equal to kappa. Okay, so the message here is the imaginary part of refractive index gives you the absorption. So if you are far away from the resonance, for example, like here, absorption is small. Away from omega naught. At omega naught, there is a significant amount of absorption. Okay, and this characteristic dispersion is shown. Okay, that the way the refractive index changes with frequency is shown. All right. So, any questions? It looked like Saurabh, you had a question. All right, it's okay. Okay. So, yeah, this is the behavior of my oscillator. Okay. Now, how does that happen? I told you, right, that epsilon, the gamma term defines your the width of the resonance. Okay. So we plotted for 3 different values of gamma by omega naught. We plotted the way the oscillator looks like, and immediately we see that as the gamma term increases, the imaginary part is becoming broader and weaker. Okay, the peak is not very strong. And similarly, in the real part, there is a stretching of this peak. Depending on how much your gamma is, if your gamma is small, then it stretches out. If you have a very strong absorption, there is a very strong variation in the real part. Okay, so green is the small amount of absorption, relatively small here, 0.25. So you have a very sharp peak, narrow peak, right? And as you increase it, let's say if you go to 1, more or less smeared out, and the same thing happens here. Okay. So this is how my absorption behaves. Okay, this is how Lorentz oscillator helps me. You might say, well, is it realistic? Well, it turns out that it is, because this is some examples of refractive indices that I've shown in the first week, I believe, wherein we showed the refractive index for various materials. And I just reproduce the graph for Lorentz oscillator from here. The only issue here is that, in the right, you are seeing this is the frequency axis, this is my wavelength axis. So I should read this graph in the reverse direction. This is my frequency, increasing frequency, right? So as the frequency is reduced, in this case, if I take this is the SiO2, right? This is SiO2, yeah. SiO2, if you look at it, my dispersion is like this, right? Why is this drop happening here? The reason this is happening is there is a strong phonon peak at 9 microns in SiO2, or around 9 microns, yeah. And at 8, I think it's epsilon near 0. Yeah, 9, okay. So now if what happens is your dispersion is displaced and it's like this, okay. So in this case, your dispersion turns out to be, there is a peak around this 9 microns, so it just comes down and then goes up and then comes down. And that is why the drop near the, this is 8 microns. That's why this is dropping here. Similarly, if I look at it, there is going to be another UV oscillator. So this is a vibrational oscillator. We all know, we talked about it. At IR frequencies, this is my phonon or vibration, right? Vibrational oscillators. Okay. Whereas if I go into the higher frequencies, as frequency increases, there's going to be some other oscillator here down, which is causing this to behave like this. Is that right? Yeah, right. Okay. Because I was just trying to see if my omega 0 and omega infinity are valid. So I'm trying to make sure that this is, if I call it 0.1, this is 0.2. My epsilon or refractive index at 1 should be greater than, at lower frequency always should be greater than higher frequency, right? R of 2. Well, okay, I should not call it R. No, I mean, you get what I'm saying here. So essentially, n at 0.1 should be greater than n at 0.2. So as you go to higher and higher frequencies, the frequency reduces. Okay. Similar trend in other dielectrics as well. So you see, now this is a different material. What is brown here? Brown is gallium nitride. Okay. So gallium nitride has a different phonon here at a different frequency. That's why the peak is slightly shifted. So all the materials you can try to explain using this graph. So this simple model of considering just a electron which is bonded to a nucleus is helping us to understand. Yes. Yeah, there's a question. Yeah.
So initially you told that we are considering the convention of equal to e power minus I omega t.
Mm-hmm.
So there is the other convention where it's e power I omega t.
Mm-hmm.
How does that impact this?
Okay. So how does that impact the graph? Well, we mentioned it in different ways. So the sign convention, right? In this case, I am assuming that n complex is basically n1 plus I n2. Okay. If you are using, okay, the question was, the whole thing was derived for a convention of exponential minus I omega t. The time dependence is exponential I omega t, minus I omega t. What if you choose exponential plus I omega t? Okay. Then your refractive index definition will be n1 minus I n2. The definition will change. So what is real, what is positive, what is negative is kind of dependent on the terminology. Okay, it has an implication because so far we have seen the real part of, the imaginary part of refractive index, right, is positive. That means there is loss. But you can also think of a material where you actually somehow manage to pump it by some other means and you have a gain in the material. Okay, in that case, my n is going to be negative. This peak is going to be down here like this. These are materials with gain. Okay. So far we have not discussed. We'll introduce them slightly later on. But in that case, it's going to be when it's negative. So it can lead to mistakes. So if you're talking about passive materials, by this convention, you should always get a plus IN2. N2 is positive. But if you talk of plus I omega t convention, then it will be N1 minus IN2, and the N2 is still positive. There's a minus there. That's it. So I mean, you can verify this just by looking at, assume that it's a passive material, put in the exponential ikx minus ikx minus omega t, right? So ikx minus omega t. Put in that basic exponential plane wave equation, put in the numbers. Put both n1 plus in2 or n1 minus in2 and see what happens. In the case of gain, so we have seen this. Oh, thank you, Saurabh, for this. So let's say in one case, you have seen that if it's a passive material with some loss, it is going to attenuate like this, right? And this attenuation is simply minus alpha x, right? But if you take the wrong convention, you'll end up getting a situation where amplifying wave like this. Okay, so my envelope is going to be that real part that's going to end up, right? That's going to be exponential plus alpha x. So wave increases in amplitude. So we should be careful about this. We'll actually put one of these in the homework. Okay, try to figure out the conventions. We'll give you multiple choice. And if you think from these basic principles, you should be able to answer it. Okay, yeah, you have any questions? Okay, thank you. All right, okay, I'm already close to 48 minutes. I wanted to make it up, but yeah, sorry, yeah, we'll just couple of more things and I'll stop. Okay. So I already have discussed this in indirectly. I said that you can have more than one oscillators, and that's what I'm showing here. So if you have any material, it's never going to happen that you have one single oscillator. You're going to have multiple oscillators. And how do we deal with that? We simply say that instead of one oscillator, you put more oscillator terms, and there is this each has a different resonant frequency. This omega j can be, for electronic one phonon, one rotational, and so on. You can have multiple oscillators. You can have multiple types of vibrations. Okay. The only thing newly I'm introducing here is that I'm saying that there is this oscillator strength, which I don't justify so far. Okay, and I won't right now. Okay. What I'm trying to say is you can have oscillators, but each oscillator need not be equally strong. Okay. There can be some oscillators which are strong. There is a very, very strong phonon absorption, but a weak electronic response. Whatever reason, the electron is very strongly bound, it cannot move easily. The phonon is like, it's very easy to have because of the way it is. Let's say if you have a polar molecule, the ionic bond is going to be quite strong. So you're not going to have that much of a strong phonon or vibration response. But a covalent bond is going to vibrate more and things like that, So depending on the vice versa, I think it's not the other way around. Okay. Think about it. Okay. So what we should make sure is you can have multiple oscillators, and I can figuratively, represent it this way. Okay. Wherein you have a vibrational oscillator, electronic oscillators, couple of electronic oscillators. The only thing is, as you go to long, high frequencies, for example, X-rays, the materials do not interact. X-rays travel through matter, right? Just because of density, you are able to see your bones in an X-ray. Okay. So the optical response is going to be close to 1 at high frequencies. But as you come to lower frequencies, each of these oscillators adds, okay, to my response. All right. So refractive index increases, yeah, this way. So refractive index increases and this, yeah. So this is how each of these oscillators behave, and all of that are actually contributing to epsilon of 0. If you take any real material, if you look at the low frequency dielectric constant, that's going to be pretty large, because each of these oscillators is adding to it. Okay. And associated with each of the oscillators, you can have an absorption peak this way. All right. And since I'm running out of time, I'll leave it to an exercise. As an exercise, I have the data from, let's say, silicon dioxide. You try to convince yourself that there are these oscillators. So clearly I see that there is an electronic oscillator here, which is contributing to this sort of a peak. And then there is another electronic. Oh no, this is probably vibrational because the frequency is low. So you have this and then another peak and so on. And whenever you have these peaks, you have a strong absorption. In between this, wherever the real part of epsilon refractive index is constant, you have very weak, there's no absorption essentially. Okay, that's why this number in log scale, that's why there's nothing here. I mean, it's lower than the measurement limit. Okay, only around the oscillators you have this peak. So, I mean, you can explain this. Any data you will be able to explain using this. Okay, so let me quickly, or let me stop here. Okay, and I'll rather, 51. Okay, let me take 2 minutes. It's all right. So let me finish this. So I can think of a situation where I can show you, I mean, these are multiple Lorentz oscillators that I have plotted with various terms. Okay, The question is which is physical, which is not physical. Okay, just looking at the expressions, right? Of course, this blue is my epsilon 1 and this is epsilon 2. So you have multiple of these oscillators. So which of them is real, which of them is not? Okay, I will not answer this. So it's a good thing to actually give it as an exercise. So we will put this in the homework. Just remember a few things. One is at low frequency, the epsilon should be higher than the epsilon at infinity. And the way the dispersion happens for a passive material should be in particular way. Okay, if you flip it, you're going to get this other one. Okay, so anyway, think about it and we will come back in the next lecture. So what I have done so far is describe the Lorentz oscillator. In the next lecture, I'll talk about how to extend this for metals. With a very small extension, you can actually explain the material properties of metals. And then we will talk about what are known as Kramer's-Kronig relations, okay, which are fundamental to understanding the dielectric response. Okay, those are some of the core things which cannot be violated. Okay, just like in physics, you cannot violate energy conservation. You cannot violate Kramer's-Kronig relations. Okay, we'll talk about that in the next lectures. So, yeah, thank you so much. Take care. Bye.